Alright, in this video we're going to take a look at cardiovascular dynamics, exercise 5 from PhysioEx. These simulations are very good because they allow you to change things, change the way stuff is working in the body without all the expense and ethics of using a real live organism and trying to set up these experiments yourself, which would take time, and you'd probably encounter some failure. So they're very good learning or lessons if you so use them. Now, this first one is looking at the effect of resistance on blood flow, and resistance specifically as defined by the blood vessel radius. So in the chapter on cardiovascular, we learned that resistance is influenced by three basic things: the viscosity of blood, the length of the blood vessel, and the diameter or radius of the vessel itself. And resistance is basically friction. It's the drag. So if anytime that there is more contact being made between the blood and the wall of the vessel, that means that we're going to use some of the forward momentum or motion to basically overcome this contact. And that way we're going to basically lose some of our flow every time we have an increase in resistance. So this walks you through a few of the things, right? And they talk about radius and length, and lastly viscosity. They show you a couple of different formulas that are mentioned in OpenStax as well to help you kind of get this idea of what all things affect blood flow. Because blood flow is ultimately the most important metric for the cardiovascular system. And we are trying to figure out all the different things that can affect blood flow, and of course how they affect it. Now the objectives are basically your hypothesis that I ask you to put in a report. So understanding how blood vessel radius affects blood flow rate. So again, that right there is your basic hypothesis, that blood vessel radius will somehow affect blood flow rate. We can then look at or think about this idea about how blood vessel radius has changed in the body, all right? And we gave you examples with the influence of the sympathetic nervous system on the tunica media, the smooth muscle, in the walls of arterioles. And then the idea of the autoregulatory and the influence of, chemicals around the blood vessels affecting the precapillary sphincters. So we have a good way to affect blood flow. But again, blood vessel radius is really going to have a lot to do with affecting that smooth muscle in the tunica media of the arteries and arterioles. So the introduction, again, kind of walks you through specifics of what everything represents. So the left beaker in this is going to be blood flowing from the heart. The flow tube between the left and right beaker is the artery, and the right beaker is another organ. Okay? So heart to other organs and a vessel between. In the pre-lab quizzes, which I don't collect but can be good telltales, you get a series of questions about blood flow, what has the greatest effect on blood flow, which of the following would not result in a decrease in blood vessel radius. All right, so that's a really good thing, and really that deep vasodilation there. The diameter of the blood vessel is the same as, right, 2 times the radius. Yep, there we go. So just making sure you understand your math. The opening of the blood vessel where the blood flows is called the lumen, and we're done. We submit that, right? But again, that's not important for us. Here's our setup, and there's our instructions down the side. So we said again, this is blood leaving the heart, going out to an organ. This is the vessel in between. So it says you can study this blood flow rate, maintain the following. So these are your constants, right? Pressure, viscosity, and length, because they could influence the outcome of this, but we don't want to change them and see their relationship. So pressure is set at 100 up here, viscosity set at 1, right, and length is set at 50 millimeters. So increase the flow tube radius to 1.5, right, beside, and hit next. Sometimes it goes straight. It says, what is the driving force for blood flow, right, and that really we know now is pressure. They like us to check that. Click start. All right, and watch. All right, and this is going to drain kind of slowly. There's no way you can speed it up, so you just kind of deal with it and let it go. And note that, again, 1.5 millimeters is a pretty small radius. And we got to move all this blood through that tube to get to this space. All right, often you just have to hit record data to give you your baseline. You have to refill it, and you have to let it go. I know a lot of students are like, oh, do we have to take this time? But again, it's not that big a deal. At the end of the day, it's basically getting this idea of relationships between these two things. All right, almost there. And there goes the last of it. Okay. So we want next, click record, we did that. Next, click refill, we did that. Sometimes you have to tell us what do you think will happen to the flow rate if the radius increased by 0.5 millimeter? So if we increase the radius, we are really going to decrease resistance. And we know that there's an inverse relationship, so if we decrease resistance, flow has to increase. So the flow rate will increase. We submit that, increase it to 2, and hit start. And clearly there is a speed. We're speeding this up a bit. Okay, we're going to record the data, we're going to refill, and again, see right away, you see, right, and here's our constants again. We didn't want to change any of those because they could influence flow, we know that, but we're interested in only looking at radius's influence. Okay, next, refill, we've done that. How does the body increase the blood vessel radius? Because this is one of our objectives. Well, we know that it increases the radius by some relaxation of that smooth muscle, right? You will now observe the effect of incremental increases in flow tube radius. Increase the flow tube radius by 0.5, click start, record, refill. So you can go through this very quickly. Record, refill, and repeat this till we get to 5. So we're going to, start, record, refill, start, record, refill, start, record, refill, start, start, record, refill, and lastly, yeah, it's like instantaneous now, isn't it? So we're seeing this phenomenal. I mean, this is not a direct, there's an exponential effect. Every time I'm just going up 0.5 millimeter, I'm getting these doubling, almost doubling effect of the flow rate. So repeat this until you've gotten there, right? Do you think a graph plotted with a radius of x will be linear? No, it wouldn't, because we already said that this is going up by only 0.5 and this is really doubling. All right, plot the data, right? And no, you're seeing that, yeah, that is not a direct or linear relationship. When one increases, right, radius increases, the flow rate does increase, but they're not direct in that sense. There's an exponential relationship. And submit. Okay. Submit to record your plot. Submit. All right. So the variable you altered was, of course, blood vessel radius. Right. These are your post quiz, and again, they don't count, but vessel radius and fluid flow. Right. So the size of the radius and fluid flow. So as we increase the radius, we increase blood flow. So they have to be direct, not inverse, and they're not linear, but they are directly proportional. All right. After a heavy meal, when we are relatively inactive, we might expect blood vessels in the skeletal muscle to be somewhat probably constricted, and blood vessels in the digestive to be somewhat dilated, again, because more flow needs to be going there. When you increase the flow tube radius, the fluid flow rate, right, make the radius bigger, the flow rate increased. Right, and then you submit. Right, and then the review sheet we're not interested in, so I said I really want you to write up your results, basically, to talk about that. But these questions are really good to help you think about what you got out of the exercise. But again, don't answer these questions in the report that you submit to me, right? And then this just walks you back through, because I didn't do what you got. All right? So, and then you could save it as a PDF and either email it to yourself through Canvas or transfer it to a USB from your computers. But that's basically, again, just showing you, reinforcing this idea that yes, radius has a significant effect on blood flow. And all you have to do, again, is present a hypothesis and an introduction to why this would be important to know, or what you thought you were going to discover in this. You take those experimental results straight out of the report, right? So just copy and paste it, and then you write up in the end what you think happened. Okay? So hopefully this helps you guys, and we'll do the stroke volume and pulse rate on the next video.